Hi guys, welcome to this channel. Today primarily we'll be talking about mechanical properties of solids. So before starting further, we need to understand that what is there in this particular module. So in this particular module we'll be learning about that how exactly materials behave, materials or solids per se behave under certain loads or under certain circumstances that they are subjected to. So now the mechanics of solids are classified into two primary groups. The first one is rigid body mechanics. Okay, and the second one is deformable body mechanics. So what are exactly these two? So to be specific about these two particular terms, rigid body motion or rigid body mechanics is certain study or analysis of a particular phenomenon where, suppose we are taking a body and now we are applying a force on it, right? So we are taking a body and now we are applying a force on it. Now we can see when we are doing a rigid body mechanics study or rigid body analysis, we are considering it as a rigid body. The 2 points or the two molecules inside this particular body, the distance between these two molecules does not change with respect to time. But when we are applying force, this body might move, but the distance between these molecules does not change with respect to time. That is, there is no relative displacement between the particles of a body, then we can call that particular mechanics or phenomenon as rigid body mechanics. But in case of deformable body mechanics, it is very important to understand that when we are applying a force on a certain body, the particles are generally displaced from certain position. That is, they get deformed. Okay, when we're applying the force F, they get deformed. That is, there is a relative displacement between the particles of a body. So this is what is known as the rigid body mechanics and deformable body mechanics. Now it is very important to understand that this particular analysis, that rigid body and deformable body analysis, it also depends on the pressure or the load range. What do I mean by that? Now suppose I am taking a particular material and now I am putting it inside water. Okay, now suppose there's a huge ocean. Now I am putting my body into this particular ocean and it is there up to a certain height h. Okay, now as we know by the fluid mechanics that the pressure that is subjected to this body is nothing but rho gh, or we say that gamma into h, where gamma is the unit weight of water. Now you can understand that when we are increasing the depth of this particular body, the h starts to change and it starts to increase. Okay, now up till here it becomes gamma into h dashed, right, where h dashed is greater than h. So as we go on further to the deepest parts of the ocean, the pressure ranges become so high that a rigid body analysis cannot be done on that particular body, though it is a rigid body. What do I mean by that is that suppose it is made of a very rigid substance like steel, like carbon steel. So when we are putting it in the surface region of the water, the analysis can be done through a rigid body analysis. But when we are taking this particular body to the deepest parts of the ocean, the pressure ranges change substantially, such that it is subjected to very, very high pressures. In those conditions, what happens is that we cannot do the rigid body analysis anymore. We have to go for the deformable body analysis. Okay. Now, the first thing that we need to understand in this chapter is to understand the elastic analysis. Elastic analysis. Okay, elastic analysis. So to understand this, I'll be drawing a ball spring model. This is a very famous model. Okay, so consider there is a ball, there are balls on the corners of a cube. Okay, there are balls corners of a cube that is connected by different springs. Okay, it is connected by different springs. Yeah, so it is connected by different springs. Now when we apply a certain force, then what happens is that the particle displaces from its position. And the springs get compressed. But when we take out the force, what happens is that this particle, which has moved from its original positions, come back to its original shape. Okay, so in this particular range, we can understand that there is no plastic deformation. We'll be talking about it later, but understand it now that in here the balls that have been subjected to a certain force, that have been displaced from its original position, comes back to its original position. So what happens is that it does not deforms permanently. When a certain materials does not deform permanently, then we might say that the structure is behaving on its elastic range. It has not gone to its plastic range. It is behaving in its elastic range. So this ball spring model is very important to visualize what happens inside a particular material, right? Okay. So now there are another two important things to understand, that what are the differences between pressure and stress. So what are the differences? You might say that the pressure is, if we put the formula, that pressure equals to force upon area, and if we consider stress, then it is also the stress sigma equals to force upon area. Okay, so they are mostly the same. If we consider the unit, then this unit is force as a unit of Newton, and area has a unit of meter square, and also here force, it is Newton and per meter square. So what is exactly the difference between pressure and stresses? Okay, so understand like this, that the pressure is primarily an external phenomenon, and stress is internal phenomenon, right? So pressure is exactly an external phenomenon, and the stress is an internal phenomenon. That means that when we are taking a body and applying some force, right, then when we are taking this force and the area of this particular body, okay, so we might say that we are applying pressure. But due to this particular application of pressure, the material of the body resists to deform itself. Okay, so for this resistance, they have to apply an opposite and equal pressure, right? They have to apply an opposite and equal pressure, or an opposite and equal force, so that they can resist. Okay, so that is why stress is nothing but internal resistive force to internal resistive area. but the pressure is primarily our external phenomenon. Okay, so this is basically the difference between pressure and stresses. Okay, now another part of the Hooke's law, another part that is important is the Hooke's law. Okay, this Hooke's law and it is a very important law because it is basically the foundation. It provides a foundation to all the elastic analysis that we do today. Okay, so it is the foundation of all of our analysis, the elastic analysis that we do. So what exactly is this law? Hooke's law tells that, write the law first. Hooke's law tells that stress is proportional to strain within proportional limit. This is not an elastic limit, this is proportional limit. Okay, the stress is directly proportional to the strain within the proportional limit. So what exactly do we mean by that? It is the stress, that is sigma, is proportional to epsilon, that is the strain. And when we remove the proportionality by adding a constant, then we add a constant to its term by E into epsilon. This E is known as Young's modulus. Young's modulus. Okay, this is known as Young's modulus, or E can be also known as any elastic constant. Okay, so it might be that it is not a linear analysis, then it will not be Young's modulus, it will be something else. But in here, this is Young's modulus. So I have said many things here, that the stress is proportional to strain and all, but from where does this come from? This comes from experimentation, and I'll go to that part. Okay. Okay. So I'll be drawing two curves. So the first curve is load versus deformation curve, right? Okay. And the second curve that I'll be drawing will be stress versus strain curve. Now, when we'll be studying, suppose we are taking this for steel. Okay, we're taking steel. Now, when experimentation is done, we'll be seeing that the curve goes to a straight line, then it goes above, and then there is a flat portion, and then goes again, and then it drops down. Okay. Now, as we know that if you think it did this way, that this axis is x-axis and this is y-axis, that we know. Now we always know that this particular axis is my independent axis. This axis is independent axis, and this particular axis right here is dependent axis. Okay, so why I'm calling it independent and dependent? Because we know that y is nothing but a function of x, and this is my independent variable, and y is dependent on x. That's why I'm calling it as a dependent variable. Okay, right. Now, if this is the independent variable and I am plotting deformation right here, so is that particular thing right? Many of us confused by this particular thing, that whether this is correct or not. That means the load is dependent on the deformation. The load that we are applying is dependent on deformation. So is it really true? That is, we are applying the load first, or the deformation is happening first. So we might get confused over here, but that is not exactly the case. This particular value of load is nothing but the resistive load. the resistive load. Now we know by the equilibrium of a particular material that whatever force we apply on a body, and the material resists with equal and opposite force, or equal and opposite resisting force. So whether we take P or whether we take PR, it is basically the same. So the deformation occurs first, then the resistance, then the resistive force is occurring due to the particular deformation that we are applying to that particular body. Okay, that is why the deformation or the deflection is in the x-axis and the load is in the y-axis, right? Okay. So now this particular region, the curve up to this particular region is a straight line. It is linear. So in this particular region, it obeys the Hooke's law, because we know that P is proportional to deformation, but that is not exactly the Hooke's law. Hooke's law states that the stress is proportional to strain. Now you might say that we can directly deal with this particular graph right here. Then why will we going for stress and strain? Now you have to understand that pressure and deformation can be different for different bodies of different shape, but the stress and strain will be same for a certain material. The stress and strain will be same for a certain material. How is that? Because the stress is nothing but PR by AR. So if the shape changes, the AR will change. The AR will change. Whether the PR is same or not, it doesn't matter. So when the shape is changing, the AR will be changing, and hence the stresses, we might say that stresses and strain are more fundamental in nature. That's why we require this particular graph. These are more fundamental in nature. That's why we require this particular graph. Okay. So it is nothing that for same material of a different shape, or a different shape body, or a different cross section, we will see that the graph is showing like this, and then is going up, and then it is showing the same nature, but for the same material is showing differently. But when we will be converting into a stress strain diagram, we'll be seeing that for particular material, the graph and the nature of the graph will be exactly the same. Okay, the nature of the graph will exactly the same. Now this particular point right here, we're seeing that the stresses, the strain are linearly dependent, that is sigma is proportional to strain. So this particular point, what we call as proportional limit, okay. So this is how the stress is proportional to strain, and this comes through experimentation, right? And this is a very important concept.